Swayam Prabha. Digital India. Educated India.
Okay, so let's get back to this proof which we had left halfway. So, yeah, so we have this claim that if, or maybe I can just recap a little bit so that we won't be lost. So, once again we are looking at this m of h and n of h, and we want to say that h likes either all residents in m of h more than all residents in n of h or vice versa. So, when comparison is concerned, we can just ignore the common residents and only talk about the ones which are different. Yes. And then we said that there is, say, r here, r prime here, and r is the worst resident in m of h, ignoring the common ones, and vice versa, that is r prime is worst in and we also wrote this claim where we said that if h likes r more than r prime, then r likes, so h likes r more than r prime, which is in the matching, so r is in the matching m, so r should like n more than m, and vice versa. So this and vice versa part we did not prove last time, and that is why we could not show that here h and y actually form a blocking pair. Right? So we did not know how to say that y likes n more than n. So that and vice versa part we will complete, and I think that will be enough for us to exhibit a blocking pair. If, yeah, so let me just write down the main theorem again. Mn are stable matchings. H likes everyone in MH more than everyone in NH or vice versa. Okay. So what this says is that a hospital also has a clear way to compare two stable matchings, and hence there is something called an H optimal stable matching. Okay, so to even say that something called H optimal stable matching exists, we need this theorem. Okay, so let's try to prove this claim first. So let's look at the set of residents and set of hospitals. So this is the set of residents, this is the set of hospitals, and let's ask each of these residents, do you prefer the matching m over n or you prefer n over m? So suppose x is the set of residents here who prefer m, and x prime is one who prefer n. Similarly, for hospitals y, we can't directly ask whether you prefer m over n because it is not clear how they are going to compare. So for now we will ask them to compare the worst in one versus the worst in another. So the comparison for H is now well defined in terms of the worst residents. Okay, so now we have a clear way to clear comparison way for hospitals. So X is set of residents who prefer M, X prime prefer N, Y prefer M, and the hospitals in Y prime prefer N, where this preference is in terms of the worst residents. And when I say worst, it is only after ignoring the common residents. So we can't say that the worst resident is same in both M and N. If it is common, we ignore that resident and look at the different residents which H gets in the two different matchings. Okay, so this is a clear comparison now. So I want to now ask, can there be a resident here and a hospital here where both of them prefer M and they are also matched in M? Okay. So maybe I will call this resident, suppose A, and the hospital, well, H. So can it happen that A and H are matched in M and they both like matching M more than N? So AH is present in M. So just the fact that A is in X and H is in Y tells us that they both like the matching M. So can there be an edge of M like this? Can N be stable in that case? So in N, A gets a different partner, H gets a different partner, but then they both like each other compared to their N partners. Right? So clearly then the matching N cannot be stable. So this itself cannot happen because this contradicts the stability of N. Right? Because A and H both like M, but then both like M over their N partners. So in that case, they will block the matching N. So N cannot be stable. But then we assume that N is stable. So then this H cannot be present in M. Okay? Yes? So X is the set of residents who like M more than N, and Y is the set of hospitals who like again M more than N in terms of the worst residents they get. But then if there is an edge of M like this, then clearly they form a blocking pair with respect to N. So what is the confusion? Yeah, so I said if they are both matched in M and they also like M more than N, then this AH will be a blocking pair with respect to the matching N. Because, sorry? Yeah, they are matched to each other in M. Say it again. Yes, so A prefers H over N of H, yes. Yes, so H prefers A. So, yeah, so when we say H likes, so we have said that H also likes M because H is in Y. So H prefers worst, that is R over R prime. Right? So R is the worst resident that H gets here, and R prime is the worst resident that H gets here. But then H likes R more than R prime, so H must be liking also A more than R prime, because R is the worst one, so A is at least as good as R for H. So H prefers A over R prime again. So yeah, so in the when we look at the matching N, H will better prefer to throw away R prime and take A, and A will also be willing to go to H because A likes H more than the N partner. Yes. Yeah, but only thing I want to say is that if A is in X, then A's M partner cannot be in Y. Yes, yes. So if A likes X, I mean if A is in X and H is in Y, then A's M partner at least cannot be in Y. Mm. Yes. Okay, so let me put it like this. So there cannot be an edge between A and H if A is in X and H is in Y. Say it again, where did we use? Yeah, so you are asking why I called that this H is in M, right? Yeah, but so this is not really necessary, but if at all this is the case that there is an, I mean, if you look at A's M partner, where can it be? So A is in X and A likes M. Can A's M partner be in Y? Yeah, so they go away. Yeah, so all I want to do is that I want to take some A in X and look at where A's M partner can be. And claim is that A's M partner cannot be in Y because in that case they form a blocking pair with respect to N. So anyone in X cannot have M partner in Y. Okay. So where are the M partners of people in X? So if people in X or residents in X cannot have their M partners in Y, they can only have them in Y prime. So all the M partners, so M of X is a subset of Y prime. Now similarly, where can the N partners of these people be? So say B is in X prime, where can B's N partner be? So can again B's N partner be in Y prime? No, right? So why? Yes. So symmetrically, if B has n partner in y prime, as in if B in x prime has n partner in y prime, then this pair will block M. So this cannot happen because this blocks M. So the blocking pairs are a little difficult to see, but that is why we define preferences in terms of the worst partners, because the worst ones can always be thrown out, and if H likes the worst partner in M over the worst in N, then H also likes, say, this B over the worst partner in M. So M of x is subset of y prime, and similarly N of x is a subset of only y, because if these people in x prime cannot have their n partners in y prime, then they should all be present in y. So any questions so far? Say it again. Sorry, thank you. N of x prime is subset of y, yes. Okay, so any more? Yes? Not necessarily. Yes. So we are asking everybody to compare only M and N. So for residents, the comparison is obvious. For hospitals, we are asking them to compare in terms of the worst residents that they get in either of the two matchings. And while doing this, we ask them to ignore the ones which are common in M and N. Okay. So because we have these two properties or these two observations, so if M of x has to be a subset of y prime should be large enough, right? So in particular, we can say that the number of residents in x is at least, now I have to sum over the hospitals in y prime. So if it was 1 to 1, we would have directly said that x should be, size of x is less than or equal to size of y prime, but then more than one resident can go to the same hospital. So we are summing up over the number of residents each hospital accommodates. Right? And let me also write down the other symmetric statement, that size of x prime is less than or equal to, when we sum over the hospitals in y, the number of residents h gets in nh minus mh. So is this part clear? We are not in the one-to-one setting, otherwise we would have directly said that size of x is less than or equal to size of y prime, because all of x, all the people in x should have a partner in y prime. But then we can't directly sum up sizes, we have to sum the number of residents matched to each hospital. And similarly for x prime. So, any question? Shall I explain some part once again if there is anything unclear? See, we have not ruled out that some hospital in y prime can get an m partner in x prime. Right? We have only ruled out n edges here and m edges here. Okay? So, but we did not say that there is no m edge between a b here and an h prime here. So, we can only say that the hospitals in y prime, they get their m partners from x, all of x, and possibly some from x prime. That is why we have put a less than equal to here. Okay. So, we have not ruled out n edges like this or m edges of this form, because we are not directly able to exhibit a blocking pair if there are edges of this kind. So, hospitals in accommodate all of x in the matching m, hospitals in y prime accommodate all of x in m, plus they may be accommodating some residents from x prime as well. So, the total number of residents these hospitals get in m is at least as large as the size of x. And because m and n are just two stable matchings, we can make the same statement for n and x prime. But what are the sets x and x prime? They are just all the residents who get two different partners in m and n. And of course, they are disjoint because either one prefers m over n or n over m, but it can't be both. Because we have just thrown away the residents who get the same partner in both. So, x and x prime, I need the next page, although I didn't want to lose this figure. Maybe I will write here. So, x and x prime together just represent number of residents that get a different partner in m and n. But then if we look at these two, so this one and this one, this is also just summing up the number of residents which get different partner in m and n. Only thing is, this is from hospital side, this was from resident side. So, we are just counting the number of matching edges, but one's from this side and one's from that side. So, in fact, these inequalities should be equalities. It is just summing the number of residents who get different partners in m and n, one's from the left side and one's from the right side. So we can say that m of x is not only a subset of y prime, but in fact m of x is equal to y prime, and n of x prime is equal to y. So this argument is a little involved, and I tried my best to bypass it, but no, it could not be bypassed, and hence we are now going over it. So what is the importance of this? So just think for a minute and see what is the importance of this observation that we just made. So the proof may not be very much visible to you right now, but at least can you see the importance of this observation? Yes? Yeah. So in other words, here we said that H likes the worst resident in M over the worst resident in N, but then so then H cannot have any M partner here, right? So in particular, if you look at any edge of this form, some R and some H, then one of them has to like M and other has to like N. So it cannot happen that both like the same matching. So although we made this comparison only in terms of the worst residents, we have shown that all of M of x is actually matched to y prime. So we have no pair RH where both of them like M and they are also matched in M. So certainly one of them likes one matching, the other likes the other matching. And now this will simplify things for us further when we actually try to show this main theorem. So any questions so far? It's a little tricky argument, but yeah, maybe you can go over it at some point and approach me definitely if it is not very clear. Okay, so now we will try to complete this whole proof. So once again, let's look at these sets, M of H and N of H, and let's see how that observation helps us. And just ignore this common part. So let me copy that observation for us. Okay. So once again, R is worst in MH minus M of H, MH minus NH. R prime is worst in NH minus MH. Suppose H likes R over R prime. So in terms of the sets that we had earlier, which set will H be? So we had these sets X, Y, X prime and Y prime. So can you say where now H will be? So H can either be in Y or it can be in Y prime. So if it likes the worst one in M more than the worst one in N, which set do we put it? Yes, in the set Y. So we know that H belongs to Y just by the way we defined the sets Y and Y prime. But then if H is in Y, where is R? So in fact Y, R and R prime, let's just pick up some arbitrary residents here, some X and Y. So what we want to show is that if H likes R more than R prime, then H likes everybody here more than everybody here, which means H should also like X more than Y. This is what the theorem claims, that if you like one resident in one matching, you should like all residents in that one matching. So if H is in the set Y, where is the resident Y? Different word? Okay, so maybe A and B I will use. Or X and Z is also okay. So let me call this as Z. Okay. Yes. So H is in the set Y. So now if you look at Z, we know that Z is matched to H in N. But what do we know? N of X prime is exactly equal to Y. So in fact, Z should be in X prime. Okay. And now we ask the question, or how does H compare X and Z? Say it again. Okay, so H should like Z more than X. But then Z also likes H. So in M what will happen? H and Z will block M. Right? So if H likes Z more than X, but then R is the worst one here. So if H likes Z more than X, H also likes Z more than R. Then H likes Z more than R because R is the worst one and certainly R is less liked than X. Right? R is the worst resident that H likes here. X may be better than that and Z is an even better one. Say it again. Correct. But then HZ form or HZ block M. Right? So if H likes the worst resident in M over the worst resident in N, it has to like every resident in M over every resident in N. Right? So we started with the assumption that H likes R more than R prime. Then we showed that for any X and Z, H cannot like Z more than X. So this thing is ruled out. So H likes R over R prime where they are the worst ones implies that H likes everyone in M of H ignoring the common part over everyone in N of H. Again ignoring the common part. So even for hospitals where they get multiple people, the comparison for them between two stable matchings is very clear. Either they like all residents in one stable matching or all residents in the other stable matching. So there is no ambiguity that they like a part here and a part there. There is nothing like that. So stability gives a nice thing here that even if there are multiple ones, the comparison is very clear. And so there is something what is called H optimal stable matching, which you obtain by H proposing algorithm. So any question here? So okay. I hope you understand the statement of the result and at least some parts of the proofs, and I think this proof is a little tricky, so going over it again may be of help. If something is not clear, you can always catch me and ask. So now we will switch gears and again we will ask, so we have seen stable matchings in one-to-one case, in many-to-one case by now. Now we ask, are these the best ones or is there any drawback that stable matchings have? So one drawback is actually that size. So let me take a simple example here. So let's stick to the one-to-one case for now. So let's go to again the men-women setting. and take a simple example here. Okay. So what is the size of a stable matching here? What is a stable matching in the first place here? Yeah, it is just A1, B1. Is there a larger matching? Say unstable one, but is there a larger one? Yes. So let me draw this A1, A2, B1, B2. The stable matching matches only A1 to B1. It leaves A2 and B2 unmatched. And now there is a larger matching A2, B1 and A1, B2. The drawback of this larger matching is that there is a blocking pair which is A1, B1. And you can of course replicate this with taking again A3 and B3, B4 and so on and so forth. Right? So we can make a bigger example, say with k many copies like this. So here we want A2k minus 1. And similarly for the B's. Right? So if we take these k copies, here also there is a stable matching of size 1. This part is actually independent of this. So there is a stable matching of size 1 and so on. So overall, if we take this whole big example, we have a stable matching which has size k. So I just took this small example and made many copies of this example and renamed the people in that. So when you execute a Gale-Shapley algorithm on this big example, really one copy of small example doesn't interact with the other copy. Whereas the maximum matching here, because it is of size 2 in each of these copies, the total maximum matching size is 2k. So when we are giving admissions we are giving admissions to students into colleges, it is not really desirable that lot of colleges have vacant seats and lot of students are unmatched just because we want stability. So in other words, it looks like stability indeed has a drawback in terms of its size. Yeah, so that is the question. So whether we should do that. Okay, so for students it seems a little unreasonable, but for doctors and hospitals it seems more reasonable, right? I mean, in the interest of running hospitals, maybe it is better to send some doctors to some unwanted hospitals. That, okay, that hospital is not getting doctors, so please go there, and such kind of compulsions can very well be made. Right? Yeah, but then it many times becomes impractical to have a complete list, right? I mean, if we are assigning, even for college admissions, you can't ask them to rank some 250 colleges. So that also becomes impractical. And on the other hand, stable matchings are not that great in terms of the social considerations. So what we want to do is we want to relax this notion of stability, and we want to ask, is there a notion which guarantees a larger size by compromising stability to some extent? I mean, we don't want to find just one maximum matching and allot people, because many people will be unhappy with that. But is there a notion which is little weaker and it gives us gains in terms of size? Yeah. So see, in stable matching, the property is that no pair of people wants to deviate. Okay. So we will compromise here, and we will say that some people may want to deviate, but majority of people don't want to deviate. So stable matchings have the property that no pair wants to deviate from it, from the matching. Now we want something called popular matchings, where no majority of people want to deviate to a different matching. Okay. So this is the notion of popular matchings that we want to see now. So here we really ask people to compare, because how do we know whether a majority of people want to deviate from one matching to another? So we just ask them to compare. So we take two matchings M and N and ask every person whether you like M or N. So let's do this to our small example that we considered earlier. Okay. Yeah. So when we ask people, each individual person, whether you like M more than N or vice versa, each person will say I like M more, or someone may say I like N more, and so on. Right? So we will get the votes of people either for matching, I mean the number of people who prefer matching M versus the number of people who prefer matching N. And what we want to do now is, if M gets more votes than N, we say that M is more popular than N. If number of votes of M is more than number of votes of N, then we say that M is more popular than N. So let's just take two matchings here. So one is our matching A1 B1, and suppose we take another matching which has A1 B2 and A2 B1. Okay. So there are these two matchings. So how would people vote for it? So which matching will A1 like? Yeah, so what will A1 say when these matchings are to be compared? So clearly A1 gets first choice in M versus the second choice in N. So A is going to say that I prefer M. Sorry, not A, A1. What about B1? Yeah, so B1 also gets a better match in M as compared to 1 in N. So B1 also prefers M. So what about A2 and B2? They were not getting anything in M. Now they are getting something. So they are of course going to prefer this N matching. So the point is, even if M is stable and N is not stable, they are here getting equal number of votes. Then N is also as popular as M. Right? So here we wrote it in terms of two matchings, that is M is more popular than N or N is more popular than M. But when do we say that a matching is popular? A matching is popular if there is no other matching which is more popular. So a matching is popular if no other matching is more popular than it. Okay, so for here in this example we see that a larger matching can also be popular, and because of the size gain here, that everybody is getting matched versus half the people being unmatched, we would actually give priority to this matching. So here these are the only two matchings. There is no other matching which is more popular than them. So both of them are popular. One is stable and the other is larger, although unstable. No, so when we define popularity, we only count the number of votes, but our goal now would be to find out a maximum size popular matching. So here it happened that the stable matching is also popular and a larger matching is also popular. Is it always necessary that stable matching will be popular? So can you try to think of an example if you think that should not be the case? Okay.